Wonderful. Well, thanks everyone for joining us. We're really happy to have you on one of our academic series webcasts. I'm going to tell you a little bit about the plan for today, and I'll just step through my outline here. And, just to make a mention that Gail pointed out too, we have a lot of webinars that are really fantastic on our jump.com events page. So certainly if you like what you see here and you want to see more, certainly visit that. And I'll show you where to get to it at the end. So today, what I want to talk about is advanced research methods with JMP, which kind of covers two sides of things: methodological, in the design aspect of your experiments or research, and also the analysis and preparation parts. A lot of what we do when we're actually analyzing data is preparing the data for analysis. So I want to show you some tools in JMP that are really appropriate for that. Now, before I launch into this, I'll tell you a little bit about my background. I'm not a statistician. I'm actually a research psychologist. And so I started learning JMP really for the purpose of analyzing research data. And JMP really makes this process a lot more straightforward for both the design and also the preparation sides. All programs can analyze data, but there's some parts of JMP that really shine for this design and preparation aspects. And so starting with the design aspect, what I mean here is before you actually collect your data, how do you decide what observations you have to collect in order to make the types of inferences you want to make? And I'm only going to cover a little bit of this. Certainly there's a lot of depth to JMP's design of experiments. It's a DOE menu you may have never even clicked before. And I just want to point out that we have a live webcast coming up on Tuesday. This is actually led by my colleague Volker Kraft, so Tuesday, October 25th, looking specifically at engineering in DOE. And we also have a great deal of on-demand and live webinars actually from the Mastering JMP series, which is a really excellent webcast series. And you'll see even the first one here is Advanced Design of Experiments. And so if you have never explored the DOE tools in JMP, those are worth watching in order to get up to speed. But what I want to talk about today is just an introduction really to some modern design of experiments using the custom designer. And something new in JMP 13 I think is really special, which is this general purpose simulate tool, which has a great deal of applications. But for our purposes today, it allows us to run some power simulations for complicated designs, specifically a mixed model. And so without getting ahead of ourselves, let's step through the custom designer and look at how we might, ahead of time, design a study that we want to collect data on. So I'm going to go to the DOE menu, and just note I'm using JMP 13, a new version of JMP that came out a few weeks ago, and I'm using it on a Mac. Of course, JMP is both Mac and PC. And I'm going to launch into the custom design tool. And the way custom design works is we're going to set up what responses we're looking to collect and what factors we're looking to measure. So of course, we need a context first. I always like to use this example when I'm teaching. Suppose we're running a wine tasting study. And so what we're actually collecting from our subjects or our people that we're asking to do this study is some wine rating. And so assume that wine rating has a limit. So we're asking on a 0 to 100 scale. And so then the question is, what factors are affecting this wine rating? And my sort of study I always wanted to run was a question of how do we think the type of closure of a wine, whether it's that cork or a screw top, is really impacting people's ratings, without respect to the type of wine. So if we were to control for type of wine, or really the brand or varietal, how do we think that's actually affecting their belief in the rating of that wine? And so I'm going to design a study real quick here. So I'm going to say we're going to have 4 factors. I'm going to click on Add Factor, Categorical, 2-level. So I'm asking for 4 2-level factors. And let me start naming these factors. So let's assume, of course, closure is going to be the thing that I'm most interested in, whether it's that cork or a screw top. But there's some other things I have to vary here and some things I might be interested in. So perhaps wine type, whether it's a red or white wine, might actually play an effect here. My intuition is that for white wines, no one really cares whether it's a cork or screw top. It's a white wine. But if it's a red wine, maybe some of our intuitions about, the prestige of red wines maybe plays into this, where we don't like the screw top versions, but we do like the corked versions. But maybe there's some other things that actually play into this and things that aren't as easy to change. Notice that with closure and wine type, I could ask a single person to measure 4 wines, one of each cork and screw top and red and white, the cross of those two. But there's some things that are hard to change about a person, maybe expertise, whether this person is a self-described expert or novice. And maybe something like gender, male and female. Notice that these factors aren't easy to change within a person. And there's actually a section here for how the changes are made. So I can actually click on that and say these are hard to make changes. Now what I'm telling JMP here is to actually design me a split plot experiment. That is, when I click continue, notice what JMP's going to say is we have a certain number of whole plots we need. Now if you're not familiar with this notation or this language, what we're saying is we have some number of individuals within which we could vary the other factors. Now the way Custom Designer is going to work is it asks us what types of effects we want to measure. And the most basic model that we can potentially estimate is one where we're looking for just main effects of each factor. And again, that notation or that language simply means, is there some average effect of closure, the screw top versus the cork, wine type, red versus white, expertise, and gender. But in this particular model so far, we haven't asked an important question that I want to know about. Do we think the effect of closure, white and red, cork and screw top, varies across the levels of wine type, red and white? That is, do we think they're the same effect of closure for each wine type? So what we have to tell JMP is that we want to fit some kind of interaction, and this is going to help JMP know what types of observations we need to make. By the end of this, we're going to get a table, simply a table we can fill out with our ratings so that we can actually run the model. So I'm going to tell JMP, actually fit all the way up to the 4th level interactions. That is, fit every interaction possible between our 4 factors. And you may have not seen it because I was clicking up here, but what JMP did was change the number of whole plots necessary and the minimum number of runs necessary to estimate this type of model. Now, if we think about it, I want to design this just as an example. And if we, let's say, have 12 people in our study, really what we're asking for is 48 observations. So for each of the 12 people, let's just ask them about each of the 4 combinations: cork as red and white, and screw top as red and white. So 12 times 4. So I'm going to have it make that design for me. Now when I click Make Design, what JMP's going to do is actually search through, in terms of its optimality criterion, what types of observations we need. That is, it's trying to decide from each of these people, from each of the whole plots, what observations do we need in order to make estimates of those parameters that I asked for. And it comes up with this design. So notice that for each of the whole plots, we have 4 rows in each of these. That is, for each person, we're going to ask them about each of the 4 combinations, right? And notice that expertise and gender don't vary within a whole plot, which is to say expertise for a person and gender of a person isn't varying or changing when we ask them about each of these wines. That would be kind of a difficult thing to change. So we've essentially designed a repeated measures experiment. A mixed model is what we're going to use to fit this, but what JMP has done is found the design that makes sense for the types of evaluations or a type of analyses we want to run. Now, the reason I'm doing this is because I want to show you this new in JMP 13 general purpose simulate tool. And so what I'm going to do after I've made this custom design is something kind of special. I'm going to go to the red triangle, and I'm going to tell JMP that when it makes the table for me, I want to actually simulate some responses. That is, I want to pretend like I know something about how big these effects are so that I can do some power calculations. Do I actually have reasonable power to run this experiment? You know, it's going to take some money. I'm going to have to buy a bunch of wine. I want to make sure I have some reasonable expectation of actually detecting the effects I want to detect. So when I click Make Table, notice what JMP's going to do is it first writes a table out for me. This is actually a table of the whole plots, the closure, wine type, expertise, and gender levels. That is, I can actually fill out this wine rating. If I just change these values to what people actually say, that's my table. That's my data. But I also got a new column, this wine rating simulation. And that column is actually responding to this little control panel here. And so what this control panel is let me set is the parameters of this model. Now, if you've never looked at sort of the parameters of a model before, this might be a little bit unclear. So what I'm going to do is I'm going to click Reset Coefficients. I'm actually going to go to Graph Builder. And here's a nice way to examine what this is doing. I'm going to take the wine rating simulated, put it into the Y, and let's look at that effect I'm most interested in. You know, how does the closure differ across wine types? I'm going to drag closure to overlay, wine type to my x-axis, and because factorial plots are often shown this way, I'm going to click on a line. Certainly in displaying data, that's not the best choice because, you know, what is the midpoint between red and white? It doesn't really make sense in a lot of cases to plot categorical with lines, but for factorial plots, that's useful because we can look for the presence of interactions based on whether the slope of the line is the same. So what I'm going to also do is I'm going to set the error over here to 0, and I'll tell you why I'm doing this. When I click Apply, what JMP's going to show me is what, based on the terms I've specified here, what the result on average is. And what you're seeing here is that there's no effect of red versus white, right? The mean here is exactly 0 and here exactly 0. There's no effect of closure because cork and screw top are right on top of each other. And we can't really see the other terms in the model yet because I haven't included them in the graph. But let's start adding effects. So for instance, let's add a 1 here for wine type, and I want you to see what response it gets. So when I click apply, suddenly now the red wines are rated 2 more than the white wine. That's what that parameter is really saying. These are called effect-coded offsets. That is, how much different from average is the red wine, the first level when I entered it into the design. And so this may be an effect we think is out there. Do we think on average in our sample, or in the population our sample is drawn from, people will rate the red wines better than the white? Well, probably. Let's just say that's true. Now, notice that the rating of 1 and -1 doesn't make a lot of sense for our scale. So we have to give an intercept here to make this a little more sensible. Let's say the grand mean of everybody who's rating wines is 50, right at the midpoint. And so I'm going to click apply now. And notice the scale changes. So we're starting to build out what our prediction is about the population that our sample is coming from. And because I've specified no error here, we're seeing this as if this is the true average. So let's start making other effects. What if there's an effect of closure? So if I go down to closure here, if I add a 1, click apply, notice quickly we get the offset of 2 above the screw top is the cork. So the midpoint of this line, right in the center, is 2 above the midpoint of this line, the screw top. And so now we've added a closure effect. On average, people are going to rate the corks better than the screw top. But remember, I had a prediction. Perhaps it's the case that people actually don't care about the type of closure when it's a white wine. And so if I go to that interaction term, closure by white, let's add a 1 there and click apply. Notice what that does is it removes that effect. I've added the interaction such that for the white wines, there's no difference in the population between cork and screw tops, but there is for red and between cork and screw top here. So I've designed a population, and remember the reason we're doing this is I want to do something about simulating power. How likely is it that I will be able to detect these differences, this interaction, and maybe even the main effects? How likely is it to detect those given that I'm sampling? I don't measure the population. I'm just going to get a sample of 12 people here. And so that's where we start bringing in error. And so notice we have 2 different types of error in the simulate responses. Error for the standard sigma, that is within a person, how much variability do we expect from repeated observations? If I were to ask you multiple times to rate the same wine, how much error around this grand mean of 50 would you observe? And then the whole plot error, which is how much different people on average differ. That is, if I'm rating or you're rating or somebody else is rating, our average rating of wines, maybe some of us are more or less critical about wines than others. So let's just make up some values here. I mean, when you're doing a priori power, you'll have to come up with reasonable estimates. This is done based on prior research. But let's just say for an individual, we'll do 4, and whole plot error, let's do 7. And so now notice when I click apply, every time I draw a sample, which is what clicking apply is doing, I get different estimates for these terms, right? Because every time I draw a sample, this is the population still, but the population has error. That is when I take measurements, I'm getting sampling error. So I'm not always going to be able to resolve the actual effect clearly. The question for power is how often will I get a pattern of results in my sample that allows me to detect or find statistically significant the terms that actually were true in the population. And that's where the simulate tool comes in. So what I'm going to do is actually I'll copy my wine rating simulated to my wine rating column. And what I'm going to do is fit a model to this wine rating column. And when I use simulate, it's going to, in essence, click that apply button for me as many times as I want and record the results. That is, record how often I get a result that is statistically significant. Now this is a mixed model. We can run it as such. I'm going to actually use an add-in, the repeated measures full factorial mixed model add-in. I'll show you where that is. That's actually on our user community. And this just makes it easier to set up this particular design. So we have wine rating as our Y. The closure and wine type are what are called within subject effects. These are our terms or factors that change within a person. Expertise and gender are between subject effects. These are terms that change across people. And then subject ID is whatever identifies the person or the whole plot in that notation. So that goes right there. When I click run, JMP will actually run this as a mixed model. If you've never seen mixed model output, there are some special components to it, like the REML variance component estimates. But in essence, this is like an ANOVA. It's a model that's actually looking for categorical differences, and we get a fixed effect table looking at each of the terms we included in our model. And notice for the one simulation we just ran, we found an effect of expertise, which actually wasn't there in the population. That's a false alarm. We found the effect of closure, which was there in the population. Remember, I had a term for that. But we didn't find that closure by, let's find it here, wine type term, 0.09. So in this case, we missed one of the terms, we false alarmed on one of the terms, and we found one. So one actual hit. The question is, for power, how often will this happen? How often will we detect things we want to detect? And how often will we accidentally reject the null on things we shouldn't? So this is where simulate comes in. We can right-click this table, and in JMP 13, there's this brand new option called simulate. And here's what simulate will do. When I click OK or click on it, it asks me which column in this particular analysis do I want to switch in for a simulated column. And JMP has already written that simulated column. That's what simulate responses did. And the number of samples here is how many times do I want JMP to click that apply button for me. And if you're going to do a simulation for power, 2500 is a great starting point. Since this is a mixed model, takes some time to run each time, I'm going to do 100 just because I want to get the webinar moving. So what this is going to do in essence is click that apply button. First, run the model, get the results, click it again, run the model, get the results, and 100 times later, we'll end up with a table made for us in JMP of all the 100 times that model was run with different samples from this population we set up, right? The simulated or the predicted population. And the resulting table looks like this. Our first row is excluded because that's the row from our original analysis. And then we have 100 more rows that show for each of those different terms, right? So if we look at this term table here, what our rows in this table are now columns in the new table. We have the p-values that resulted from those 100 little experiments we ran, given some population that we specified. And again, for a priori power, we have to have reasonable estimates for these things in order to really run it and trust our results. So these are all p-values. And remember, we reject the null if we get a p-value lower than some criterion, some alpha value. And so we can look at the distributions of these p-values for each of the terms we care about in order to realize or figure out what our power was and what our false alarm rates were. So I'm going to click this preloaded script, this power analysis script, and what this does is runs distribution. And for each of the different terms or for each of the different sources in our model, effect sources, it's shown us the distribution of p-values. So let's look at what our model really was in the population and what we got after our simulations. Remember, closure had an effect, so it was 1 here. Our p-values had this distribution, so distribution you get if there really is an effect. And notice that for our rejection counts at alpha of 0.05, we rejected the null there about 36 times. Well, exactly 36 times. 0.36 is our rejection rate. So our power here would be 0.36. Not particularly great if that's an effect we really want to detect. Closure by wine type was an effect we wanted to detect as well. That was the interaction term here. And we rejected that null only 26 times, or a rejection rate of 0.26. This is pretty terrible power. If we're going to spend all this money to have all these people drink wine, we probably want to collect more subjects because this is not looking good for us if these really are the magnitude of the effects that we're looking for. And let's look at a term that didn't actually have an effect. And so if we look down at simulated power for expertise, where we didn't put in an effect, we get power that's 0.1 here. If we were to look at our rejection rate here, it should be 0.05. So if we ran more simulations, it would normalize to that. But for any term that doesn't actually have a real effect, we're expecting about 5% of the time, or 5 out of the 100 simulations, to reject the null. And that's just the price we pay for taking a sample. And so notice that this was a not terribly complicated model, but it was a mixed model, something that is not typically easy to do power calculations for. And really, no matter what the design was from Custom Designer, we can do this simulation process in order to calculate power or to simulate power. And so this Custom Designer and the sort of the modern approach to DOE gives us a lot of tools to make that table, and then that simulate tool lets us do a lot with it. And there's many more things we can do with the simulate tool, which some of our other webinars will look at. So again, check out our other DOE webcasts if you want to look more custom designer. That was a very quick and simple example using it, but it's a very powerful tool for designing your experiments. All right, so the next thing I want to talk about is really a very time-consuming part of most research, and that's preparing your data for the analysis. And analysis, it turns out, for the most part, for advanced research, doesn't actually really be that complicated. I mean, mixed models are complicated in a sense, but the tools using them are not that complicated to run. But preparing data requires kind of a little bit of skill and a little bit of art. And the first I want to talk about are detecting and finding outliers. And so I'm going to pull open some sample data. These are available under the Help menu, under Sample Data. And this is a whole set of serials. And the reason I like this example is we just have a lot of columns, and I think we have intuitions about what observations we should get for serials. So this is an easy one to work with. Now, when I say outliers, I mean points that are extreme enough that we don't trust they were entered correctly, or points that are so extreme that we think they'll influence our model in an undue way. Now, you have to be very careful with outlier detection. Do this not after you fit models and seen whether your hypotheses are confirmed or not. We have to be very careful not to only find results we want to find. And outlier detection should always be done before you've even determined whether your data supports your hypotheses. And we can think about outlier detection in several ways: univariate outliers, multivariate, and subject level. And so I'm going to talk about each of these sort of in turn. So by univariate outliers, I mean outliers that are strange with respect to the column they're in. So a point here, let's say for protein, if we had apple cinnamon Cheerios listed 20 as its protein level, even if we're just looking at a table, we'll be able to see that easily. But oftentimes outliers are hard to spot just looking at the table, and that's where distribution as a platform becomes very useful. And so my standard procedure whenever I get any new data table is actually grab all the columns that I'm interested in, put them into Y, and click OK, and go through one by one, just checking that the distribution looks as I expect it to look. That is, if I scroll down, it becomes very obvious when there are points that are very strange with respect to the remainder of the distribution. So for instance, for fat here, if I hover over this point, natural brand oats and honey, it's very high on fat relative to the rest of the distribution. And the reason there are points here, the reason the points are actually shown for these serials is because they're beyond what's called the outer fence, 1.5 times the interquartile range plus the third quartile. And so those points are selectable, and this is actually a really useful feature. If you're new to JMP, everything gets selected when you select points, including the rows in the data table, which means I can operate on these as if I've clicked on them in the data table. For instance, I can right-click and exclude them. I can give them a marker. Maybe I'll give them a star, and this way I can identify them. Notice the table is updated with that marker. Or I can do something which is my favorite. I can name this selection in a column. If I select this, JMP asks me what the new column should be labeled. I'll say high fat. And if they're selected, I want that new column to get a 1. If unselected, a 0. And notice when I scroll to my table, I now have this new column that allows me to make those selections later on. For instance, I can right-click on the 1, select matching cells, and now I have my selection back. And so what I like to do is actually go through each of the different columns and just find points that I think are a little bit suspicious. This is not me excluding them. This is me just giving myself data for later to find points that are a little bit weird. So high fiber and complex carbos, everything looks okay. And so this is a nice univariate approach to looking for outliers. When you have a great number of columns, under the columns utility section, now it's under columns, I think we actually moved it under predictive modeling. Where did we move? So we just actually moved all of our menus around. But there is a way to do basically a screening for outliers. And so by especially when you're working with very large data sets, it's going to be a lot easier to look for those outliers in more of a sort of large scale way. We put it under the screening menu here. So under screening, explore outliers, especially when you're working with a large number of columns, this becomes a little bit simpler. But before getting to that, let's actually look at sort of a different approach to looking at outliers, which isn't this univariate way, this way with respect to a single distribution. And that's what I'm going to call multivariate outlier detection. And multivariate outliers are outliers that are strange, not with respect to their own distributions, but with respect to really where they fall relative to a bunch of other variables and the relationships among those variables. And so for instance, let's go to Analyze, Multivariate Methods, Multivariate. And multivariate as a platform is sort of like a generalization of distribution. And I really like the multivariate platform. If you've never seen it, let's just grab some columns, click them into Y. These have to be numeric because sort of the basic idea of multivariate is to come up with the covariances and the relationships among these variables. So you start off with a correlation matrix, and you get the scatterplot matrix as well. And my interest here for multivariate outliers is to look for the points that are strange with respect to the relationships among the variables. And so, for instance, if we have a strong relationship here between potassium on the x-axis and fiber on the y, the points that are sort of outside this little ellipse are points that are strange with respect to that relationship, right? They're a little bit too high relative to how much potassium they have. And so when you have points that are outside, and notice the points I marked before actually are outside the relationships in bivariate space here, when you have points outside of that, they give you a little bit of cause for concern in a different way. Not that they're extreme in any one dimension, but that they're extreme in two or more dimensions. And so if we want to capture extremeness in terms of this n-dimensional space here, we have a lot of variables all at once. If we could plot them all together and look in some ellipsoid, which points are outside of that, that would be great. It's very hard to plot more than 3 dimensions. So what we can utilize is something called a Mahalanobis distance. And that's under the red triangle, outlier analysis, and Mahalanobis distance. And a Mahalanobis distance is a type of covariance scaled distance. That is, it's looking for the points that are not just distant from the centroid, the multivariate mean, but ones that are distant in a way that doesn't really make sense. Just like a point that's really high on fiber, but not really, or high on potassium, but not high on fiber, or the opposite. So points that are sort of outside the general relationship. And so if I turn on that Mahalanobis distance, what we get is the distance plot. What we're looking at in this plot on the x-axis is the row number. And so this is literally the first row in the data set, second row in the data set, third row in the data set. And then the y-axis is the Mahalanobis distance, that scaled numeric distance measure, and again, scaled in terms of the relationships, that is the covariance structure. And points that are above this upper control limit, if I can just select them here, so points that are above this 4.16, that's the number that changes based on how many rows you have. Points that are above that are ones that are sort of too far to be expected. That is further than we would expect by random sampling, with some, given assumptions about how these things are distributed. Now, again, these aren't necessarily outliers. They're just points that are a little bit strange relative to the relationships among all the variables at once. And so even though you don't see them sort of coming out in the two-dimensional plots, remember, this is taking into account all those variables. And so again, I can grab these points, right-click. I can do a name selection in column. And maybe I'll say, hi, Mahalanobis. And this is something I can look into later, whether these influence important relationships. The best thing to find out about your outliers is that whether they're included or not, whatever important effects you're looking at don't matter. What you don't want to find out is that when they're included, your effect is there, and when they're not included, your effect isn't. Right? So you have to be really careful about those situations. All right, so that's a great way to look for multivariate outliers. Now, there's sort of a different type of outlier I want to talk about, and this is one that's often harder to find, and these are subject-level outliers. And to sort of motivate this one, I'm going to bring up some data I collected for an experiment a while ago. This was actually looking at how I could influence people's predictions of credibility of products they're doing shopping online. So this is actually, I'll show you what the design looks like. Suppose you're shopping for health supplements on Amazon. And on these pages, sometimes you see graphs that are two-dimensional showing the data, tables showing the same data, a terrible three-dimensional plot showing the data, or just an image sort of about the information on the page. If you were to see these pages, certainly if you saw a 4, you would realize the manipulation here. But across people, do people who see certain instantiations of data make different sort of judgments about the credibility of the information on the page? And these were all pretty well controlled, and the data was actually already on the page, so it's just a matter of re-showing the data. So the question was in the study, does the instantiation of data actually make an effect, or is it just the fact that data is presented? And so we measured a number of different things and measured them across many different products. We actually wrote the script to spoof the Amazon page, so we had undergraduates come in thinking they were shopping. Research is sometimes like that. So the question is here, do I have subjects that are potentially what I would call bad subjects that didn't take the task seriously? And I had some additional information that became very useful for me. How many seconds it took for them to view that Amazon page, and how many seconds did it take for them to rate on these 7 criteria that Amazon page. And so I want to show you something that I found really useful when I was actually doing this research and writing it up. And that's under Tables Summary. And if you haven't used the Summary tool, this is a great way to just do quick summarizations on data here. But what you can do is actually summarize on the basis of some grouping. So in this case, subject. I want measures for each subject on some statistics. And specifically, let me take viewing and rating and ask for the mean. What's the average time across the 25 products they rated that they took to view and the time they took to rate? And the reason I want to do this is when I click OK, Jump's going to go through my table, and it's actually going to calculate for each of my different subjects. Right, I did it twice here. For each of my subjects, the average view time and average rating time. And so this gives me some sense of their attention. Now here's what I like to do. So I'm going to right click, I'm going to do sort and sort ascending. And notice I have some subjects here, subject 407860132, who on average spent only 2 seconds looking at pages in my study. And if I go to distribution, and look at the distributions for time viewing and time rating, just like I did for univariate outliers, I can quickly see there are some weird ones. Here's somebody who on average took 2,000 seconds to make ratings. This is actually somebody who just let the page time out when they were doing the study. And we had people who on average took 400 seconds, 433, to make the viewings of the page. And so this is very interesting. This gives me information about sort of subject attentiveness and what they're doing in the study. And so this first subject clearly is not going to be good. Took 2,000 on average to rate and 2 on average to view. Notice by using Tables Summary, this table is a linked table. That's why these are locked. That is, if you look on the left-hand side, I've actually selected in the original table this subject. And so if I go to my original table, I'm going to do next selected. Notice that this is that person's data. And if I look across, clearly they didn't respond to anything. They took no time to rate and they just let it time out. So I can go right click, hide and exclude. So I don't want to include those data in any kind of analyses. Now let me show you another way to do this. I'm actually going to bring back these data. And this may be not as obvious of a way to do this, but if I go back to Table Summary, I'm again going to put subject as my grouping variable. Now, let's say credibility was my most important measure. That's the one I wanted to see if it got moved around by these different sort of graphical elements or the instantiations of data. Now, instead of looking at the mean rating, which of course is what my models will look at, I'm going to look at the standard deviation. That is, I want to know across the 25 objects or 25 different pages each subject rated, how variable was their ratings of credibility? Because if I click OK, and I go and sort again, let me sort ascending, if there are people that have 0 or no variability, that is, they gave exactly the same responses or no responses at all, well, that's a problem. And if I have people that gave very small variability, that is, they rated every single thing the same, then that's probably also a problem. That means they just clicked from each page to each page and kept saying 3, 3, 3, 3, 3. Again, looking at the distributions here gives us information about sort of how much we should expect. And notice that the distribution of the standard deviations, this would be kind of chi-square shaped, right, has a center. So on average, people are about 2.13 in terms of their standard deviation across measurements. And we have some limits. So I can actually come up with good criterion, when do I want to exclude observations? Well, maybe if they're in the lower 0.5% of variability or lower 2.5%. So I could actually, in a sense, Windsorize or do a trimmed sample based on people who actually gave me some meaningful information, not ones who just rated every page exactly the same. And this generalizes pretty well. So let me go back to my original table and go back to summary. Let's actually take all the sort of dependent measures. I'm going to ask for the standard deviation of each of them. And then I'm also going to put subject as my group. And what I can do is get an average measure across all the measures of how variable they are. That is, I'm going to take these columns, I can right click, and I'll talk about this later in the sort of making new variables section. There's instant formulas in JMP. So with them selected, new formula column, combine, and let's actually take the average. Now I get the average of, and this gets tricky, average of the standard deviation of the measurements each subject made. And I'm going to right click, let's do sort ascending, and now I can find the people who on average had the lowest variability across all the measures. Again, looking at the distribution makes this a lot more clear. We can see on average who these individuals are that are giving very, very similar responses from each measure. All right, so that's subject level. And so looking at the variance and certainly looking at the mean things, if you have time rate and time view, that becomes very important. And certainly know that if you use something like Qualtrics, which is a great survey tool, you can embed timers. And so that's actually how I did some of these. And so you can time how long they are on particular questions within a block or within a page that you show them. All right, so very useful. All right, so that's subject level data. So now calculating new variables is something that's very important. Certainly if I go back to serials, sometimes we don't maybe care about certain variables until we do calculations on them. So in fact, in here, notice we have cups per serving as a column. And so if I'm looking at the number of calories, well, maybe I want the number of calories per serving. I don't care about the number of calories if they're not scaled to be the same. Some of these servings are more and less in terms of cups. So I want calories per cup. And so in JMP, there's a formula editor. And so if you make a new column, and hopefully you found this if you're a JMP user, right-click and click Formula, and you can define a formula for that column. That is, I can actually take something like calories divided by, just hit the divide key, and cups per serving. Hit apply, and now I get that scaled measure. And so the formula editor is really fantastic. It actually can take advantage of all the JSL scripting, so you can actually write code within a formula to evaluate in the column. And notice we have some really advanced things. We can do conditionals. We can also do sort of the comparisons, and statistical procedures are all in here. And so certainly take advantage of the formula editor when defining those formulas. But there's also instant formulas, which become very useful when you want to do these calculations quickly. And so, for instance, the cups per serving, let me scroll back over to calories. Those are the two columns that I want to involve in a formula. Actually, let me grab calories and cups per serving here. And so with them both selected, you can right-click the first one. And remember that new formula column that I used to make the average before? Well, there's a lot of different ways we can combine them. We can do the ratio, right? So the first divided by the second, which is what I actually want to do. The reverse order. We could do averages, differences, and all these kinds of things. So if I click ratio, again, JMP will make that column, and it does it in the same way. If I go to formula, it's actually made the formula in the column. It didn't just write the values. And so that's actually a very useful way to make these formulas quickly. And we also have options like standardizing, and this I actually like quite a bit. These are all on very different scales. If I right-click all of them, new formula column, distributional, notice we can center them, subtract the mean off from each, standardize, subtract the mean off and then divide by the standard deviation of each. We can range them from 0 to 1. We can do transformations like the Johnson normalizing or do other things. I'm going to do standardize. And notice what this writes is z-scored columns for each. And so now these are actually on the same scale. So if I wanted to make comparisons across sort of extremeness for each, I can actually do that. So that's instant formulas. Now it's worth noting that you could do temporary formulas as well. So if I go into, let's say, Graph Builder or any kind of launch window, if there's a particular formula I want to make, but I just want to make it for the purposes of this graph, for instance, maybe I want the log of calories. If I right-click, go to transform or any operation, if I click log, notice what JMP will do is write this sort of italicized column. And that's actually temporary. I could drag it in and use it in an analysis, but it doesn't live in my table. The reason why is it's living just in this window right now. If I right-click it, notice I have the option to add it to the data table, or I can rename it and do other things by it. So this is a nice temporary way to make a formula when you're just inside of a platform. And that actually works all across JMP. So that's temporary variables. Now, one other thing you're often going to find yourself doing, especially before running analyses, are creating new variables that bin by either intervals or by percentiles. And there's a number of ways to make these binning variables. Maybe we just want a high and low calories kind of column. Not something categorical like we have here, but something that actually just bins them. So there's a number of ways to do this. Under columns, you actually have the option under utilities to make a binning formula. And the binning formula is rather nice. That is, you can actually set for specifically with bins, really where you want and what labels you want for each of these different values. And so if I have a bin width of, let's say, 150, and let's offset this at 0, maybe that's the two bins we want. So offset sets where the bin starts the first time. The width is the width of the bin, so how wide each ones are. And so we see we have two bins here, since we had a nice range. And so if we actually create this as a formula column, we actually have these now as a categorical distinction, whether they're 0 to 150 or 150 to 300. Now, that's not always the way you want to do your binning. Sometimes you would rather bin in a way that's based on percentiles or based on cut points that you design. And so there's this interactive binning add-in, and I'm going to show you where that is in the community in just a second. But interactive binning is really quite nice, since this is an add-in that you just specify the variable you want to work with, lets you actually draw these cut points interactively, and it's going to show you what proportion you're cutting off. And so if I want to cut points at particular places, I could simply do that by clicking Add Cut Points, and I could even give these a name. Now, under the red triangle is where you can actually save these cut points to a grouping column, or you can do things like set the cut points at percentiles. So potentially, I want to make 4 cut points, so I'll set it at 0.25. So JMP will do its best to put that proportion in each of the different cuts. And so interactive binner is really quite nice. And so if you go to the JMP user community, it's doc 20 or 6237, you can actually just search for interactive binning on the JMP user community, community.jmp.com. And that's also where you'll find that repeated measures add-in that I showed before. And so interactive binning is a really handy tool to have installed. All right, so there's some additional things we can do. So subsetting and merging, this is something we often find when we're first combining data together. That is when we first get data and we need to bring them together into a final data table. I always like to show this one. We have this US demographics data table. It's some sample data, but it has some columns that you would clearly know we never found this table online somewhere. This actually had to be created by bringing together measures from multiple places, right? There's no table online that has household income and also the number of smokers maybe in the state. So we've essentially joined tables together. And so imagine we started off with a bunch of individual tables, just the attributes of the states. So things like gross state product, vegetable consumption proportion, things like that. Basics of the state, IQ, the region, the population, educational characteristics of the state, and also the household income for each state on average. And so pulling these tables together before JMP 13, we do this using a join. And join is a very powerful platform that allows us to specify, joining the income column with something else. Do we think or do we know that there are columns that match? And so state in both of those matches. And so we could actually specify this and set up the joining. Now, this would be an iterative process. We'd have to join each table with the final table until we bring all the columns together. But I want to show you something new in JMP 13, which is the JMP Tables Query Builder. And Query Builder is a really fantastic tool under the Tables menu. Query Builder was originally built for pulling against SQL databases, which is something you can do in JMP. But what Query Builder lets you do is specify a first table. So it's picked up income as my primary table, since that's what I opened first. I can add these others as secondary tables. So education, basics, and attributes. And then what JMP does is it searches through those tables and does its best to find a marker or a column that is matching between them. And so it's found that key. It knows that state is a common key between them all. And so if I click on the table snapshot, notice it's going to do a great job combining these. That's the original table it's going to pull back together once it pulls in education, basics, and the attributes. So when I click Build Query, JMP will actually go to a next section. I can tell it what columns I want to have for the final data set. I'm going to click Add All. I can set up the characteristics of it. It even actually writes me the SQL code. So if I wanted to pull this against a database somewhere else, that's actually the code that it's using to make that. And so if you're teaching SQL, that's quite handy. I can set up filters right now, but I'm just going to click Run Query. And by run query, I mean pull together those different data tables and put them all into one. And it's going to keep the identifier from each. So we have state 3, 2, 1 here. We don't really need all of those since they all match, but JMP does that so you know where those tables start. But notice it's pulled together the tables for us. So it's a great way to pull together multiple tables. So that's again under the Tables JMP Query Builder. I want to show you something else that's new in JMP 13, which is actually quite impressive and gives you a lot of flexibility when you're working with large lookup tables. Suppose we have this table, our basics table, but we want to bring in some of the attributes from our other table. And so what's really powerful about this is I can specify a link ID in one table and right-click and specify a link reference in another table. So I'll just point it to that reference. And notice what happened really quickly is I got a little key attached here. So in the first table, I just told the table what column is identifying the rows. And then in my final table, I just said, well, where do you want to look up values from? And I said, hey, look in that other table, the basics table. And what it did is it added in this little section here, and it said here are some columns that are referenced from the other table. That is, they don't actually have to exist in my final table, and yet when I go to, let's say, Graph Builder, and I want to use some of these columns, let's say I want to make a map and I actually want to use the IQ in the states to make that coloring, right? This is referenced. This doesn't exist in my final table, and yet I'm able to use the data from those columns. And that becomes a very powerful tool, especially when you have lookups. Suppose you have an item number and you have a huge database of items. You don't want to join that against your actual final data table. You can actually just link the items. And so maybe that's useful, in research situations, especially when you have lookups for particular characteristics. So again, the way that works is in your table you want to reference to, you specify the column as a link ID, and then in the table you want to bring the values into, you link reference it to that table. So that gives you that ability. And this can actually be done in a nested. Maybe we actually have another link here. So region could actually reference to something else. So another table that's linked to it. So we can eventually form really chains of links across tables. All right, so those are tools for subsetting and merging. Now for reshaping and restructuring, there's a number of great tools in JMP that I want to just point out really quickly. Stacking of tables. Sometimes you have tables such as this, where your observations are across the columns for each different unit of sampling. If we're going to analyze this with a mixed model, we actually have to have these across rows. And so just be aware that under tables, we have the option to stack and split. And I'll show this rather quickly. When you stack columns, you're simply selecting the columns that make up the different observations. Those are your stack columns. And I don't actually have to change anything else. I'll click OK, and notice what JMP does is it now stacks the column, the original HIST 0, 1, 3, 5. Those were the original column titles. Those are now in this new column called label. And the data from each of those, 0.4, 0.2, 0.1, 0.08, those were the original observations for that first dog here. And so we've just taken a table that's 16 rows and made it 64, because for each of the different dogs, there are now 4 rows making up those 4 original columns. And so stacking is how you get your table into that sort of long format. Now the inverse of that is splitting a table, that is taking that stack table and reversing it. And then also times when you really don't need to stack or split, but you're really just tabulating. And I just bring this up. This is an example I usually go to, a situation where you have 8 observations for each state on SAT scores that you've measured across different years. But if you want to run a regression, let's say on just the salary in a state against the average SAT score, and you don't want to do it in some specialized way, you really just want to average over maybe those scores across the 8 years. And under Analyze, the tabulate platform is a really nice way of doing this. Much like summary, we can make tabulations based on our data, but I like the graphical version of this because we can simply drag and drop columns. So if I drag state here, notice JMP builds a table. It says how many rows do you have for each state? It says, okay, you have 8. Let's say we actually want to look at, let's say expenditure. I'll drop that in the center and ask JMP to calculate the mean for me by drag mean on top of sum. So I want the mean expenditure across those 8 years, and I also want SAT total. Remember, I can do instant formulas. I showed you before. Right click. Let's do combine and take a sum. So SAT verbal plus SAT math. Now to add this to the table, I'm going to drag it not on top of expenditure, but just to the right. And so what I'm going to do actually is sort of add it to the table. Oh, it doesn't want to add there. Let's see if I'll just do one of these. I'll do one of them for now. So once you've actually made that table, this is actually a tabulation of the table. If you click the red triangle, make it into a data table, this will actually write out that table as a JMP table you can analyze. So with 50 states plus the District of Columbia. And so this isn't so much a restructuring as it is a tabulation that was necessary to do the analysis. And so be aware that tabulate is sometimes something you use before you get to the final analysis, especially when you're working over repeated observations. All right, so that's tabulation. Now, just in the time we have, I want to point out a couple of specialty things within the JMP tools. And so under Analyze, and so advanced fit model options, there are times when we're running specialized multiple comparisons. We've already looked at mixed models. I want to show some options in multiple comparisons rather quickly. So this is a data set sort of based off of real data I collected. I used to time how long it took me to get to campus when I was teaching. And so I had not this many observations. This I made for a class. But it made this factorial combination of the time of morning I left, the different routes to campus I took, and the day of week. And so let's fit a model in fit model rather quickly because I want to show you some tools you may not have known were there. So I'm going to put in my time to campus in seconds. I'm going to take each of these variables. Now, under model effects, if you've never used fit model, what you're designing is which effects in the model you want to include. This is a full factorial. Each of these factors has crossed, so I actually want to fit all the possible crosses. When I click run, JMP produces the basic fit model output. I'm going to hide some of the sections because you may have looked at the effect test sections, but maybe you've never expanded effect details. And what effect details do is for each of the different terms or sources in the model, it's going to show us the means for the different levels, and under the red triangle give us a number of options. And so maybe you've turned on least squares means plots before. This gives you the plot across the different days of the week for how many seconds it took me. But maybe you've never explored these other options, and there's two I want to point out today. So the least squares means contrast brings up a panel that can be a little intimidating at first because if you don't know what it's doing, it's not entirely clear, but it becomes a very powerful tool. And what you're really putting in here is little indicators to say which mean from any of these five do you want to compare against another mean. So the way it works is you give a plus to anything you want to compare to anything given a minus. So for instance, Monday versus Tuesday looks like that. 1 versus -1. Now the 1 and -1 is not a prediction of the mean, but it's really a weight in a linear contrast. And without getting into the details, these have to sum to an absolute value of 2, and each side has to sum to, or the total is 0. So they're balanced on either side. So the left-hand side versus the right-hand side. When I click done, JMP actually produces that test. And so this is the test of Monday versus Tuesday. But we could do complicated things with these. I'm going to do another least squares means contrast. So for the same term here, looking at day of week, what if we wanted Monday versus the average of the other days? Well, I'm going to click minus for the other days. Notice that they all get the same amount, so 0.25. So the sum of all these is still 0, and the sum of the absolute values is 2. So we're sort of keeping a balance. On the left-hand side 1, on the right-hand side 1. When I click done, that gives me that test. So we're basically doing weighted means. So Monday versus all the others can be done in the context of this model. And so that becomes a really powerful tool when you want to make specific comparisons. So another thing you can do with linear contrast is what's called a slice. And I'll cover this rather quickly, but let me do the day of week by route plot. And so this plot is for each day of week, which are the different colors or the different lines, each of the different routes. And let's say I want to test a sub-design analysis of variance. Is there a difference between the days of week for the different routes? So within First Genesee, comparing these means, within Gilman Drive, comparing these means, within La Jolla Village Drive, comparing these means, and within Nobel Drive, comparing these. That's a sub-design analysis of variance. That was 4 of them. We also have 5 other sub-designs. Within Monday, is there a difference between the routes? Within Tuesday, is there a difference between the routes? Right, so those are all sub-designs. And within the red triangle, this test slices option is what that is. And when I run that, we're going to get slices for Monday, Tuesday, Wednesday, all the way through Friday, and also slices for Genesee, Gilman, and the others. Now let's interpret one of these. The slice for Monday is a question of, do the routes differ on Monday? At the slice, meaning at just that part of the design, is there a difference for the other factor? Similarly, if we look at the slice for Genesee, that's a question of, okay, just considering Genesee, is there a test or a difference across the different days of week? And so these sub-design analyses give me the ability to break up within a bigger model tests of smaller things. And so test slices is certainly something to utilize. These are actually all linear contrasts on their own. And so if you look at the way the slice is formed, unless you're really familiar with these, you don't have to expand this. But that's essentially what it's doing. It's simply a test of, for each of the different sections, what's the test across the other variable. All right, so those are testing slices. Now, we won't have time to get into it too much, but bootstrapping is an option in JMP. Anywhere you see something you want to bootstrap confidence limits for, you can simply right-click, and you'll have a bootstrap option. That's available also in JMP Pro. Similar to Simulate, but this is actually taking a bootstrap sample, so repeated samplings from the same data to give you estimates on confidence limits. And then, of course, JMP has many other options. We can do validation, model comparisons, partial least squares, and generalized regression, very specialized tools that some of our more advanced webinars will cover. Okay, I said I definitely wanted to give some time for questions, and I know we just went through a lot. And remember, this is recorded, and I'll send out those recordings to you, but I'm going to pause and see if Gail has any questions that have come in. It's a great question. I'm really glad you asked that. So with slices and with those types of comparisons, it isn't. And that was actually a section under here I didn't have time to get to here, the alpha corrected methods. Let me recall here and bring this back up just so everyone knows what was asked here. So let's go back to a slice when we had a lot of comparisons. So day of week by route was a good example. So we had a lot of comparisons here. And if I right click and make these into a combined table, you can see we actually had 9 of them. So 9 slices. So this is an uncorrected p-value. Now there are some things I would do here, since you can't really get the same types of tests by running something like a Tukey HSD. That'll compare every single mean against every other mean. That's a pairwise comparison. That would be alpha controlled, but in this case, the slices are what we want. So there's a great tool. It's the false discovery rate correction. So this is also in the user community, and so this employs FDR correction, so false discovery rate p-value. And the way this works is you simply give this sort of platform launch the effect, and so in this case, actually let me give term and level. That's what identifies what the actual comparison is here. And the p-value column, probability F, and when I click OK, JMP will make a new table. That's actually the FDR adjusted p-values for each of these. And so they're so extreme at this point, it didn't really change too much. But certainly those things that are borderline, that's really worth considering. So multiplicity, of course, becomes a huge issue, especially with research where you're really, not running a pilot study. This is, the primary confirmatory research. And the place to find this, go to community.jmp.com and go and search false discovery rate correction. So I'll search false discovery rates. That's actually, we'll get there. And so once it searches, you'll get the false discovery rate p-value. And this is an add-in that'll actually work for any table that you have p-values in. And so this would be my general purpose p-value correction. So you don't necessarily have to do it with something like a Tukey. You can actually get your table of p-values and correct given the domain of inquiry that you're in. And certainly you could do it experiment-wise or within particular measures. So hope that helps.